Okay. Okay. So this is the first time I use this interface, so I hope it works. Mathieu, do you have a question? So there should be a text interface to ask questions. I don't know if it works. In any case, we'll start in 5 minutes from now.
Ça va? Ça roule?
Yeah.
T'as démarré la fusion?
Yeah.
Good. C'est bon, il a démarré.
Can you hear me? Can you answer in the chat if you hear me? Great. So let's just wait 5 more minutes. Hello? Okay, so we'll start in 2 more minutes.
I'm going to disconnect the
Okay, so welcome everyone. We'll start very quickly. So I think this is the first ECO webinar. And during this webinar, I will talk about PDI, the Parallel Data Interface, which is a library that has been developed in the framework of this project, a library to decouple applications from I/O concerns. So this is a collaborative effort. Many people have been involved, and I thank them all. So, including all those people cited here on the slide, but other developers, you can see the list of the full list of developers on the PDI website. So, a library to decouple application from I/O concerns. Why do we need that? If you look at the I/O ecosystem for HPC, there are many available libraries, including plain POSIX I/O, or NCC or library with the printf style I/O. There is a similar API for Fortran. You have MPI I/O, of course, libraries like HDF5 or NetCDF. They both have either a sequential or parallel version. You have libraries that are dedicated to checkpointing, like FTI, SCR, and then you have more advanced, let's say, libraries like XIOS, CyanLib, IME from DDN, Damaris, Adios, etc. So there are many different libraries. The question is which one to use, and when we look at what we want the library to be easy to use. We want it to be fast and offer high performance. We want a library that is easily portable from one architecture to another. We want a library that offers a large language support. Maybe we use our main code is in C, C++, or Fortran, but then we do post-processing with Python. So we want the files to be accessible from both languages. We'd like ideally a file format that is independent of the parallelization we use for the execution. We'd like the file to be portable from one architecture to the other. We don't want to only be able to use the file on the architecture where we generated it. And there are many more requirements actually. But when we look at this list and when we look at the IO libraries, what we really have is a kind of pick 2 out of 3 situation. So that is, we cannot have all these features together. We have to make some choices. So which one to choose? To answer that question, I will take a look at one specific code. This code is Gisela 5D. It's a code for plasma simulation developed in CA RFM in Cadarache, France. It's a gyrokinetic code that runs on very large parallelism with a large memory footprint. So, for example, on the Curie machine, it uses more than 100 terabytes of memory. In this application, there are two kinds of I/O. On one side, we have diagnostics, and on the other side, we have checkpointings. So diagnostics are the results of the simulation written all along the simulation that contain the result that the scientists want to use. And the checkpoints are used for two purposes. One is for we have on one side intermediate checkpoints that are written along the simulation, and at the end of each run we have final checkpoints. The intermediate checkpoints are used for fault tolerance, so if the application crashes along the simulation, we are then able to restart it, while the final checkpoints are used for segmentation. You can only run a simulation for something like typically 10 to 24 hours. This is a limitation of the computing centers. And so if you want to run longer simulations, which is the case for Gisela 5D, you need to write the checkpoint at the end of this time and then read that checkpoint to restart a second step of simulation. And the requirements for these two types of I/O are different. If you look at intermediate checkpoints, you want performance. You can use fast temporary storage that is node local. You want to overlap with computation with simulation. But the main goal is performance here. You don't want to spend too much time on writing these checkpoints. For the final checkpoints, there are other requirements. You want the file to be portable so as to be able to restart on a different machine. You want it to be file decomposition independent because maybe you want to restart with a different level of parallelism. You want them to be permanent, that is to write to permanent storage, so the parallel file system, and not to local storage inside the nodes. So you have different requirements. The requirements for the diagnostics are even different. Even more different. But all of these requirements I listed are for production runs. If you look at debug cases, when you just run small debug cases for development purpose, then the requirements are yet again different. And you want, in this case, to have something that is easy to manipulate. This is the most important. So what we see is that even if in a single code, we have really different requirements for different parts of the code, which means maybe the library that is the best suited is not the same for each part of the code. So when we take a library, we have to make a choice. Do we want the library to be stream-oriented or to offer an object API? Do we want an imperative API or do we want a declarative API? Do we want a general purpose library that can handle any kind of I/O, or do we want a domain-specific library that is very efficient for one specific kind, like checkpoint writing? Do we want to be able to use dedicated hardware nodes or specific hardware like NVRAM, SSD, etc.? What kind of file format do we want? Do we want one single file or do we want one file per process, etc., etc. These are all the kind of choices we make when we choose a library. So, as we've seen, there are many different libraries. In one single code, we have many different requirements, and the library that provides the best answer to each of these requirements might be a different one. So it's a complex question what library to use in a parallel code. And if we look at the life cycle of a code, it's even more complex, because when we start the code, we want to use a very simple API, but then when the code starts growing, we start having requirements in terms of performance, with different requirements in different places, as we have seen with the Gisela case. But then we port the code to a new architecture, and maybe the best I/O strategy is a different one, because we move to a new architecture. And maybe the libraries we chose in the first place are not the best one on this new architecture, or even are not available on this new architecture. So the goal in our case, the goal of the PDI approach, is to minimize the change required in the code along the evolution of such a development, and in order to be able to keep one version of the code, even with different libraries, with different requirements coming from different parts of the code, or from different status of the development lifecycle. So we introduce PDI, and when I hear someone saying something like that, this is what I think of. This is a comic from the XKCD website. So I told you there are many different libraries, and this is kind of a mess, and my answer is to provide a new library. Is that a good idea? Well, we're not exactly in this situation, because PDI is not an I/O library, it's an interface. It's a coupling interface between the main code and the I/O libraries. It doesn't provide any I/O capacities. So let's look at the way we've designed PDI. When we look at the I/O stack, we have the user code, which is typically, in our case, a parallel MPI code. This user code calls an I/O library. This I/O library might use more nodes than the main code, and this I/O library offers an interface with the file system. If we look inside, we see there are many actually subparts in this inside the library. So there is the first part that is hidden here, but inside the code we might need to adapt from the user code domain-specific concepts to the I/O library API. Then we have the actual API that provides stuff such as opening a file, closing a file, writing. So here we can have either stream-oriented writes or object-oriented writes. We specify the distribution of the data in case of parallel API, etc., etc. Then we have a front end that runs on the same nodes as the user code, and that does the first step of work inside the same nodes as the user code. We can have the use of burst buffers inside the local node storage. We can have compression. We can have some data processing here, etc., etc. Then we have the implementation of a parallel strategy. That's where maybe the library will redistribute the data, and maybe for some libraries use a different set of nodes than the nodes used by the main code. So maybe here you will also do staged IOs or stuff like that. And then we have a final part of the library, which is the backend. In this backend that runs on maybe, as I said, a different set of nodes than the nodes used by by the main code. You might have yet another step of buffering, and this is the step that does the actual write to the file system and that chooses the file format, etc. So if we look at this big picture, what does PDI do? Basically, the idea is simply is an implementation of the API part, and it leaves all the rest. So as I said, PDI is not an IO library. It only implements an API. It's an IO interface, not library. So the idea of PDI is first to standardize a declarative API that can be used by the codes, then to use a configuration file to describe the actual IO we want to do. So in the code, you don't say anything about the type of IO, what kind of things you want to do. You just declare the data that is available. Then you have a configuration file that is PDI specific on the side that specifies what you want to do with the data. And then there is a plugin system that is available in the backend, and that is the solution used in PDI to interface with the existing libraries. So the idea is really to reuse the existing libraries, IO libraries, and to provide an interface, a common interface that can be used with any library, because we offer a very high-level API. So what are the choices we've made in PDI? Earlier in the presentation, I've listed a set of choices any IO library has to make. And I said this is a problem because depending on the part of the code, you might want one or another of these choices. So in PDI, we've made the choices related to the API only, and we've left all the rest to the actual plugins. So basically, all the rest you can choose by choosing the plugin that that offers the library you're actually interested in. So the choices we have made are those related to the API. And in that case, we've made the choice to offer the highest level API possible. So we stay as close as possible to the concepts manipulated in the code. So do you want a stream or an object API? We chose an object API because in your code you manipulate structures, arrays, etc. The stream concept is really an IO concept. So in the API, we only expose to the library the object manipulated by the code without doing the transformation to a stream. We leave that to the plugins. Then do we want an imperative or declarative API? We've chosen a declarative API because in that case, we just declare what we have, what is the data available from the code, and we don't say how we want to write it. Once again, this can be chosen in a second time. And the final question was whether to have a general purpose or domain specific API. In our case, we've chosen a general purpose API where you just declare the data that is available. And since you don't say anything about what you want to do with the data, it's really not a domain-specific API and can be, this way we can interface most of the available IO libraries. So this is what has guided the choices made in the library. And now I will talk a little bit about the library itself. So let's see what the library API looks like. The first two functions available are the initialization and finalization functions. These are very simple functions. The initialization function should be called at the start of the initialization of the code. It takes a reference. The PC3 conf parameter is a reference to a YAML configuration file where you specify everything you want to do. And it also takes MPI communicator. This communicator is used because, as I said, some I/O libraries use dedicated I/O nodes, and in the API, what we do is basically we modify the communicator, so we might steal some nodes from the communicator, and the idea is that the communicator you get after the call to PDI init only contains the compute nodes and not potential I/O nodes. Then the finalization function simply releases all resources used by the library. So let's see in a very simple code how to use that. So this is a very simple code. What it does is I think, oh well, we don't have the computation function, but we have a main loop that is the time stepping, and then we have some initialization before and some finalization after. In this example, there is no PDI at all. So let's see the first step to use PDI. We just have to add our two functions we've seen, the initialization function and the finalization function. Then the second part and the main part of the API is the share and reclaim API. So the idea is to expose data to PDI. The share call takes the name as a constant string, so the name of the data that is shared. This is just an identifier that is used to identify the shared buffer along the simulation. Then we pass the actual address of the buffer, and we provide an access that can be either PDI out, so basically you want to write data, at least you want to provide it to PDI, so it goes out from your code and into PDI, or PDI in, which is the opposite. You want to read data, that is, you want data to come inside your code from PDI. The idea of this PDI share call is that before this call, you had exclusive ownership of the buffer whose pointer you provide. After the call, the buffer is shared with PDI. So basically, you're not able to modify it. You're not allowed to deallocate it after you've done a PDI share. This PDI share means we are both the main code and PDI are co-owner of the buffer. And the PDI reclaim does the opposite. So you pass the name, the identifier of the data to this PDI reclaim, and you get sole exclusive ownership of the buffer again. So basically the idea is you compute some values in an array, then you will share it so as to make it available to PDI to write to disk or to do whatever you want. And when you start reusing the buffer for computing the next time step, let's say, you do a PDI reclaim. Typically in codes, most of the time, what we've observed is that the PDI share and PDI reclaim come just one after the other. So we also provide a PDI expose that does exactly that. PDI expose is nothing more than PDI share, then PDI reclaim of the exact same buffer on in one single line of code. So basically, before the call to PDI expose, you have exclusive ownership of the buffer. After the call to PDI expose, you have exclusive ownership. But during the call, then the library is able to use the buffer to write it to disk, read it from disk, or do whatever it wants with, and whatever is specified in the configuration file with the buffer. So let's see on our example what we do with these calls. So I've added a few PDI expose to the code. So basically, we expose everything we compute along the simulation. And the idea of this PDI expose is that it does nothing by default. You can add PDI expose in a lot of different places. And since it doesn't do anything by default, it's never an error to do a PDI expose. As long as you know that the data is available, that the pointer you pass is valid, you can do a PDI expose of this buffer. Then the second part of the API is the notion of event. An event can be triggered with the PDI event call. An event is nothing more than notifying the library that a specific location has been reached in the code. So the different plugins can react to these events if they want. Once again, a PDI event has no effect on your code by default, so you can add a PDI event basically anywhere. And a second thing is the transactions. The idea of a transaction is to group multiple PDI expose together, because sometimes the plugins will want to use different buffers together. So maybe a post-processing plugin will want to compute the sum of two arrays, let's say. If you want to use two buffers together, it's not possible with the simple PDI expose. A simple PDI expose will share the first buffer, then reclaim it, then share the second buffer and reclaim it. If you put this PDI expose inside the transaction, then the transaction will ensure that all the buffers are shared first and reclaimed in a second time. So you have share the first buffer, share the second buffer, reclaim the second buffer, reclaim the first buffer instead of interlacing. So let's come back to our example. In our example, I just add a few events. So for example, a loop start event just before starting the main time loop, or and I also add the transactions to ensure that when I have multiple PDI expose, they are grouped together, and the plugins can use them together if they want. As you can see, the transactions also take name as parameter and identifier as parameter. This is the name of an event that will be triggered by the transaction. So, as I said, this API from the code, basically you specify very little information. The only thing you specify is the address of the buffers where you have computed the data along the simulation. So basically, it's very little information, and you don't say at all what you want to do with the data. This information is provided through the PDI configuration file that is passed to the initialization function. Here we see an example, the smallest possible example of a configuration file. In this configuration file, the first part specifies the type of the data that is exposed to PDI. In this case, we specify first the metadata. Metadata are small values that PDI will keep along the simulation. So PDI will make a copy of this metadata to be able to reuse them along the simulation. So for example, here we see that the iter buffer contains an integer. And if we go back to our example, we see that when we do the PDI expose for the iter identifier, it's a reference, it's a pointer to the ii variable, which is an integer, the loop index integer. Then we have data. Unlike metadata, data is not copied by PDI. It's a passing by reference only. The idea is that most of the data you compute along the simulation, you don't want to trigger extra copy of this data because maybe it will use too much memory, or maybe it will use time that is in a useless way. So the data, the type of the data that is specified, the idea is that you specify this type, but it will not trigger any copy. It will just specify the type so that plugins can use the data when it is available, but by sharing the buffer, not by by copying and working on a copy. So in that case, we see that the identifier main field contains double, and since it has a sizes attribute, it is an array, and in that case, a 2D array. See, so if we come back to our example, we see that the main field is indeed the cur is provided by the cur variable, which is a 2D array. And the size of the array depends on other values from the simulation, and these values are actually provided by the metadata. And in the types of the data, you can actually reference the values of metadata with this dollar syntax. So basically, you can provide information about the size, the stuff like that, from the metadata information. And the last part inside the configuration is the loading of the plugins. So in this example, I've loaded the dechdf5 plugin, which offers a declarative API on top of HDF5. And I said that I want to write data to the file whose name is output, and then the rank of the current process, the MPI rank of the current process. So this rank is metadata provided by the code .h5. So we will use a sequential HDF5, one file per process. And we say that we want to write the main field. So the main field is the reference to the value, the data that is shared with PDI. We want to do this not at every iteration, but only when the iteration number modulo 16 is equal to 0. So that is every 16 iterations. And we want to do that to write inside the data set whose name is iter with the iter number / main field. So basically, we can reuse metadata in this configuration again. And in this example, I've shown a very simple example of configuration. But if you look at the documentation, you can see that declarative HDF5, the dec HDF5 plugin, covers a wide range of HDF5 features, including parallel HDF5, writing sub-slices, etc., etc. However, this is not always enough. Sometimes maybe you will want to use features that are not covered, features of the HDF5 library that are not covered by the dec HDF5 plugin, or you will want to do some computation that only you know about. For example, you want to transform the data before writing it to disk or whatever. In this case, there is another plugin which is called user code. And what does this plugin do? It calls your own function. So for example, in that case, I said that when the event testing is triggered, I want to call the test function by passing it two parameters, the iter number and the main field. Iter will be available by the name in1 and main field by the name into. So what does it do? This configuration simply calls a C function, or you can write it in any language with C compatible API, so that covers quite a lot of languages. This function has to take no parameters and return nothing, but inside the function you can access the actual parameters you've specified, so in that case in1 and in2, and get them inside your own variables. And once this is done, you can actually use this data in any way you want inside the function. So you can call HDF5 with any very complex parameters if you want, or you can transform the data, etc., etc. If you transform the data, of course, you can also expose the data back to PDI to make it available for further processing. So this is the main user API. So what we've seen is that the PDI enables to replace IO library calls by PDI calls with only two concepts. The first one is the concept of event. So basically, you specify that this is a place where you accept to transfer control to PDI plugins. And the second one is the concept of sharing buffer. So basically, with zero copy, you just provide a name, a pointer to the buffer you want to share, and an access right. And this makes it possible for plugins to use the buffers provided. Then PDI provides two levels of API. The high-level API is the one we've just seen. It also provides a more thorough low-level API that can be used by plugins, where they can be notified by when an event is triggered. They can be notified when a buffer becomes available. They can access any information available in the configuration file, etc., etc. So how difficult is it to write such a plugin? It's actually very simple. All you have to do is to implement one class that inherits from the plugin class, the PDI plugin class, where you have two virtual functions you can override. The event function is a function that notifies you that an event has been triggered, and the data function is a function that notifies you that some data becomes available. So this is a C++ API. Plugins are written in C++, and then you have to just call a simple macro to register your plugin with PDI. So this is really, really simple to write a PDI plugin. So what is the current status of the library? The library is publicly available. We have a few releases, and the last one, 0.1.4, is about 1 month old. There are currently 4 plugins available. The user code plugins that enables you to write any function to use the data provided through PDI. The HDF5 plugin that allows you to access a large part of the HDF5 features. The Cyan plugin that is similarly developed for the Cyan library, and the FTI plugin for the fault tolerance interface library. PDI is available under BSD3 closed license, so it's very permissive. You can use it in any of your codes. I want also to talk about the fact that the library we really want to be production ready. As I will show in the next slides, we use it in the Gisela code, but we also have a strong testing effort in collaboration with PSNC, and in that case I really want to thank Carol and Thomas that work in the context of the ECO project to make the library rock solid. We currently have more than 178 tests running at each commit in the library. And so the library is really developed currently, but we really believe our testing procedure ensures that it remains very stable. And if you want to get started with the library, there is a tutorial available that focuses especially on the HDF5, decouple HDF5 plugin, and that will show you how to use it going from very simple use cases to use cases with parallel HDF5 writing slices, etc. And as you will see in the plugin, it's really short in terms of number of lines of code to configure PDI with the decouple HDF5 plugin to use to do even very complex stuff. So, in order to evaluate the library, we've implemented checkpointing in Gisela with PDI. To do that, to do this evaluation, we've implemented 4 versions of the Gisela code. A version that doesn't do any checkpointing to serve as a baseline. A version that does checkpointing using HDF5, which is the main version in the code before our work. Then we have a version that uses a dedicated fault tolerance interface, FTI. And finally, we've made available, we developed a 4th version that uses PDI to interface. And through PDI, we are able to use either to use no checkpointing at all, to use HDF5, to use FTI, or to use HDF5 plus FTI together in the same code. So here I look at the implementation cost. It's very difficult to evaluate the implementation cost, but what we look at here is the number of different functions called and the number of lines of code. So on the left, we have the case where we use the native API, and on the right, the situation where we use PDI. If we use the native HDF5 API, we have to use 24 different functions for a total of 535 lines of code. The same thing in PDI only takes 3 function calls. As I've said, it's very simple. It's 207 lines of code, but in PDI, you also have to implement a configuration file, in that case, 172 lines of code. So all in all, it's a slightly less lines of code, but it's not a huge difference. But then we have the FTI version. FTI offers a declarative API, so it only requires 7 different function calls with 216 lines of code. And FTI also requires a configuration file, but since it's domain specific, FTI only focuses on fault tolerance and checkpointing. It's only 29 lines of code of configuration. In PDI, if we want to switch from HDF5 to FTI, we only require 37 more lines of code that provide and that require 2 additional functions, because in that case we have to group the expose inside transactions, as I've shown earlier, and 7 lines of configuration. So basically, the idea is that switching from HDF5 to FTI when we have when we use PDI is really easy. And finally, we wanted to try HDF5 plus FTI. Using PDI, it's really easy. We only add 3 lines of code to specify when to use one or when to use the other one. with the native API, it would have been very difficult to do so, and actually this is not something that has been implemented. We've only implemented it through PDI because it's so easy. So that is from the ease of use point of view. The goal of PDI, once again, is not to make the library easier to use. We only rely on the existing libraries, so what doesn't go inside the code goes in the configuration file. But the advantage of PDI is that it's really easy to switch from one library to the other. So this is from the implementation cost point of view. What about performance? What is the overhead of using PDI? So we first look at the memory overhead. So this is the execution of the Gisela code on the Mare Nostrum cluster, either with or without PDI. And what we see is that the numbers are really similar. The first figure is for node checkpointing, so whether we use PDI or not, since there is no copy of the data, there is really no memory overhead. Similarly for HDF5, in the HDF5 case, HDF5 allocates a few buffer on its own, so we see that the memory usage changes along the simulation. But this is really something that is not due to PDI, and PDI, the version with PDI offers the exact same behavior as the version without PDI. And it's the same situation for the FTI version, where the use of PDI to interface with FTI doesn't increase the memory requirement. Once again, this is due to the fact that PDI does no memory copy. Then the second aspect of performance evaluation is the time to solution. So in that case, we've done once again an execution on the Mare Nostrum cluster with and without PDI, and we've changed the size of the problem from a very small problem to a very large problem. So what we can see is that there are, of course, differences in terms of performance between the different libraries, but for one specific configuration, whether we use PDI to interface with the library or not, doesn't make any difference. So in blue, we have the case, the base case with no checkpointing at all. In black, we have the case where we use HDF5 for checkpointing, and in red, the case where we use FTI. In that case, FTI offers a strategy that scales way better than HDF5 because it relies on node local storage. But in that case, where we have a very small problem, it's not very interesting. So what we see is that for small problems, HDF5 is a good choice, either through PDI or not. But then we chose to do a different experiment. We scale in terms of number of nodes, and we look at the behavior of the different libraries, once again, either with or without PDI. And once again, we see that whether we use PDI or not doesn't make any difference. For each curve, the version with PDI or without PDI is really the same in terms of execution time. What is interesting is that the best choice in terms of library is not the same depending on the number of nodes you use. So basically, the idea is that PDI will enable you to use the best choice at any level of scalability, because it's so easy to switch from one implementation to the other. You just have to replace your configuration file. So that is really the advantage of PDI. You have no memory overhead, no execution time overhead, and you're able to use the best suited library at in any situation. And for different parts of the code also, as we've seen with the combination of HDF5 plus FTI. In that case, HDF5 plus FTI uses FTI for intermediate checkpoints because FTI enables the code to overlap communication with computation, while for the last and final checkpoint where we are interested in checkpoint portability, we rely on HDF5. So in that example, we see the advantage, the real advantage of PDI, the ability to choose the best strategy depending on the part of the code, but also depending on the machine we use and the number of nodes, etc., etc. So to conclude, I've presented PDI, a library that enables to decouple I/O from the main simulation codes. PDI offers a declarative API where the codes only provide data pointers, and the type of the data behind these pointers is defined in a YAML configuration file. PDI only provides optional calls in the sense that the code remains valid without the PDI calls. So basically, the PDI calls, their default behavior is to do nothing, and they add very little overhead. Then we have the actual IOs that are declared that are plugin specific. So basically, if each plugin has its own configuration format to describe what you want to do with the data made available to PDI. This is described in the PDI YAML configuration file. And we currently offer 4 plugins, the HDF5 plugin, SignLib plugin, FTI plugin, and user code plugin. But as I said, PDI is actually not only for I/O. There are many things you can do through the PDI coupling approach. I've shown fault tolerance, but you can also do other things such as using it for debug, visualization, post-processing. It's really easy to do post-processing through PDI. With the user code plugin, you can write your post-processing calls and either run it together with the code or run it independently from the code, writing the data to HDF5 and reading it from HDF5 before post-processing. You can do code coupling, etc., etc. So PDI is really a coupling API, and not you should not only think of it as an I/O library API. So if you're interested in this library, you can join us on the Slack PDI channel, where we can discuss with all the PDI developers. Thank you for listening to me, and if it works, I will take questions. So I think there is a button to raise your hand if you want. And there should be a place where you can ask question, text question, which I think should be the preferred version. So if anyone has any question, please. And if not, thank you for attending. Okay, so we have a first question by Maxime Delorme. Thank you for this nice presentation. Thank you, Maxime. Can you talk a little bit more about the compilation time? Compilation time, the compilation of the library itself takes, I don't know, it's quite small. It takes less than 3 minutes. I don't remember exactly the compilation times. It really depends on how many cores you have available to do it. Compilation time for the main code, you just add a few calls to C functions. So it doesn't add any very, very, very little compilation time. It's really not something. It's not the library is developed as a C++ library, but we make available a C API and a Fortran API. We also have a Python API planned. So a C API typically incurs very little compilation time overhead. This is really not something we've had problem with the compilation time. Did we, Agostino Funel asked whether we tried PDI with other codes. We've tried PDI with other codes in-house. So we have 2 codes where we use PDI. These are quite small codes, not very large codes as of now. We have, it's planned to use it inside a code called Compass, which is a parallel code for geothermal simulations. So this is the current situation, but we're really happy to collaborate if some people want to use it on other codes. It's also planned to use it in different codes in if the Eco2 project is accepted. This is really something we want to target. I mean, we don't want to be a research project. We really want to be a production project. So when codes want to use the library, we take the time it requires to provide support to these codes. Thank you. Well, I don't know if there are any other questions. Well, if there is no other questions, well, thank you all for attending. I will stay here for a few more minutes if someone wants to ask questions, but if not, thank you everyone for attending this first ECO webinar. And well, I think there will be other webinars. I don't know what the subject will be, but please stay tuned and read the mailing list to know about that. Thank you, everyone.